Hello, everyone. Nice to meet you all. Welcome to this talk on LLMs. A lot of what I'm focusing on is actually going to be how they remember, how they kind of think, and then an element of that within cybersecurity, mostly on like data exposure. Um, my name is David Dixon. I'm the machine learning specialist and research lead at Hertzian. Hertzian, we've been using AI and a variety of large language models for the last 10 years to analyze free text data from across the internet for our clients. Our main focus has been the games industry with our product Player XP and all-in-one community analysis dashboard for understanding the complete conversation in video game communities. We have also worked with the NHS and other health service providers with Patient XP, and we also offer a generic solution in Customer XP. The main focus of today is the T in GPT, which stands for Transformers, a neural network architecture introduced by Google in 2017 paper, Attention is All You Need. There's a wide variety of models that can be built using transformers, from voice to text to voice, text to image, machine translation, pretty much whatever you can think of. The specific version that I'm going to focus on today is the type that underlines tools like ChatGPT and DeepSeek, which is a model trained to take in a piece of text and then produce a prediction of what comes next. So we're going to look at also a few other bits, but how they work, how they remember things, why it's so important to consider what we're telling these models when we use them from a security perspective. But there's two important things to highlight before we begin. Firstly, most importantly, I'm not in cybersecurity. Beyond the basics of what to do in like a workspace as I as an individual can do, I'm not specialized within it. So as you guys will all know more than me, I'm going to focus more today on the technical behind the scenes aspects of artificial intelligence systems. There is, of course, a growing concern of generative AI's role in social engineering attacks with deepfakes and mimicry of writing style, leading to impersonations. This is a bit more complex, and probably the domain of policy and training and identifying for people to combat. So instead, I'm going to focus on the bit I'm more confident with, which is data exposure and AI. And secondly, there's going to be a lot of little white lies and oversimplifications. This is quite a big topic and the focus of many PhDs. We don't have time to get into all the details, but also fundamentally, we as humans don't fully understand how large language models and other large scale AI systems work. We know what they're doing, we know why they're doing it, but how it's identifying and storing trends in the data is a bit beyond human understanding. What I'll be taking you through today is a high level version of the fundamentals and the latest research into understanding AI from Google DeepMind, released a little over a year ago. Now, as I said earlier, transformers, specifically large language models, are designed to give it a piece of text, predict what word will come next. Initially, this might sound a little bit different from generating paragraphs of content, but a simple way to make this generate a longer piece of text is to have it predict the next word from the initial text, then run it all again to make a new prediction based on all the text, including what it just added. This repeated prediction is what happens when you interact with ChatGPT and see it produce one word at a time. To begin to understand how LLMs actually do this, we need to start at something that is not quite relevant. Well, it's very relevant to transformers, but isn't actually new, and that's embeddings. An embedding is a representation of a word, its relationships, and the concepts around it in vector space, and it's at the heart of how AI transformers see, process, and understand language. It's also used for images, audio, or videos, but we'll just discuss word embeddings today. To begin any process, a transformer will convert your text input into a big list of vectors. For instance, the sentence, the tall purple alien boarded their sleek red ship, would be converted into a list of vectors for each word. It's very useful for these systems to have everything represented as real numbers, because then you can do things like calculus on them, which is at the heart of training AI. These embeddings will be constructed from a predefined, very large vocabulary identified algorithmically at the training stage on vast amounts of text data. In doing so, you get some interesting behaviors that emerge. For a start, words with similar meanings will have embeddings that are similar or close together, such as the word for daffodil being in a cluster of similarly bright, colorful flowers. But this vector space also allows the model to capture more than just word similarity. It also represents the complex relationships between words. For example, in this form, the operation of female minus male yields a vector. This vector or direction can be added to dad to get mum. This kind of demonstrates how embeddings can encode concepts such as gender into a direction. These concepts or directions encode everything from familial relationships to relationships between country, capital city, associated food, the idea of plurals, adjectives, so much more. Naturally, these are quite hard to visualize completely. We can visualize things in 3D space quite easily with a limited number of directions. But these embeddings don't have 3 dimensions, but thousands and thousands. GPT-2 had 12,000. And while we don't know GPT-3 and GPT-4, the very recent GPT OSS has about 100,000 dimensions. And I'm sure you can understand why more dimensions for more directions to encode more relationships is a useful thing to have. The representation enables the model to understand the context and meaning of words far beyond simple string matching, and has been commonplace for natural language processing since it was kind of founded and created in 2013. So we've defined how AI sees and interprets the words we give it. Let's explore how it thinks. Similar to how our brains have identifiable sections dedicated to kind of different aspects of thought, you know, your cerebral cortex, the left, the right, stuff like that. Within a large language model, there are 2 elements that represent its brain. Each represents a different kind of memory. You have the attention layers for short-term context, and then the feed-forward layers for long-term knowledge. The attention layers within the transformer model act as the short-term memory, its ability to understand the context of the conversation. From the embedding, each word is assigned attention that enriches its data by passing contextual information from other words throughout the message, allowing the model to understand the nuances between phrases and sentences, identifying the deeper meaning of the input. This is how the AI remembers part of what you've already said, but also how it explores the kind of the context of what you're saying. It's in these layers that allow the model to weigh the importance of different words and their surroundings and sequence. When processing, it's where it recognizes the difference between different words that share spellings, such as bat and bat, or mole and mole and mole. It's where it collects adjectives, verbs, adverbs, and associates relevant information with nouns and characters. It's this mechanism that enables modern AI systems to have such a rich understanding of text, as the model can process all parts of an input simultaneously rather than sequentially. To go back to our earlier example, in the sentence, the tall purple alien boarded their sleek red ship, through an attention model, the descriptions of the nouns, the height, the color, the shape could be encoded. But more than that, the tone, the style of language, concepts of ownership, that alien implies not of Earth, so it's probably a spaceship, not a pirate ship, or that the alien was outside beforehand. All of these are being added into the embeddings, with new directions building to a much more complex and complete vision of the input. To expand on something from earlier, a large language model's prediction is actually only based on the final embedding, the final word. As such, imagine that the text that we input was almost an entire mystery novel. all the way up to the point right near the end, after all the detective work, after all the investigation, which reads, therefore the murderer was blank. If the model was going to accurately predict the next word, that final vector in the sequence, which began its life simply embedding the word was, will have to have been updated by all of the intention blocks to represent much more than that single word. It would have to somehow encode all of the information from the full context that's relevant to predicting the murderer. That's a very quick look at what attention models do. It allows transformers to give a depth of understanding beyond the words written on the page. However, attention layers only answer what's known within the context. The next question is, how can an AI know the answers to a question you ask it about trivia, history, or coding? If you feed a large language model the phrase Michael Jordan plays the sport of blank, the model should hopefully correctly predict basketball as the following word. This would suggest that somewhere within the model's hundreds of billions of parameters, it's stored an association between the specific person, Michael Jordan, and his specific sport. Anyone who's played around with one of these models has a clear sense of the sheer amount of facts it's memorized. But where it's memorized it is the big question. In December of 2023, a few researchers from Google DeepMind posted some good work on this question using the same examples of matching athletes to their sports. Although a full understanding of how facts are stored remains a little unsolved, we have some good foresight and knowledge into how this is being done. In contrast to the attention layers that handle concepts, the feed forward layers where LLMs appear to store long-term knowledge, where facts are primarily stored, it's kind of difficult to fully understand why LLMs answer how they answer. We believe that these layers act as the long-term knowledge to allow large language models to retrieve and apply facts to these embeddings, to bring in concepts and patterns learned from their massive data sets, enabling it to generate its like informed, comprehensive responses across vast ranges of topics. The easiest way to imagine what these blocks are doing is that each individual embedding in parallel is being asked a series of questions and being encoded with information based on the answers. The full encoding is the result of essentially asking many millions of these questions and recalling all of the facts related to the yes answers. For instance, one of these questions might be, does this current vector represent or relate to London? Then encoded in the result would be the vectors or directions for United Kingdom, the Great Fire, Ferris wheels. Any related facts would be introduced into the context here. In terms of parameters, the feed-forward layers make up approximately 2/3 of a transformer, and the depth of the knowledge that can be stored within these vectors of numbers encapsulates all of what these LLMs know. As such, understanding precisely what these layers are doing is quite challenging. All of these questions are isolated from each other. They're interconnected, interwoven, and not being asked directly. It's because of this immense complexity and obfuscation in this process that we don't fully understand AI. This is what leads to unexpected things, potential vulnerabilities being undetected, and biases left unknown. So we've just covered a very, very quick overview of how memory works in LLM. And you might be aware that there's no point where I mentioned how they're learning. So how are they actually remembering these facts? Training is not done as you use an LLM, but in a separate process. The majority of training for a transformer is an automated process where given human written examples of text compares to how well it's able to replicate them. But for generative capabilities, additional human feedback is occasionally given on whether a response is good or bad, and the output is adjusted to either continue giving similar responses or to change the response to something else next time. Both of these processes need a lot of data, and for LLMs, the companies that created them spent years crawling the internet and collecting all the data they could get their hands on. And now they're beginning to exhaust that well. This is why APIs for collecting data have shot up in cost, and why they're looking at data before 2020. Training the next generation of AI is becoming more complex, and the best source of trade data is the content we're providing it directly. Anything we give to these systems won't be remembered immediately, but will be stored by the owner to trade down the line. I can pretty confidently say this, especially as in the UK's Code of Practice for Cybersecurity of AI, it lists system operators shall log systems user actions to support security compliance, incident investigations, and vulnerability remediation. If you're storing them already, why not use them to train as well? So when you provide these details about yourself, work, or other confidential information, this new knowledge will be presented to the AI to trade and learn eventually, not immediately, but eventually. The specific details and words are not listed as files within the network, but the descriptions, relationships about you, about any confidential information, are stored as patterns in the matrix of its mind. So removing these things are also incredibly difficult. It knows about me. Even if your data has not been used to train, it's also too important to remember that because so much potentially personal information is being stored by these AI companies, they are prime targets for attack. ChatGPT had a security breach in March 2023, leaking user information, conversation details, and digital messages. DeepSeek had a complete security flaw with important information requiring no authentication to access, meaning attackers could have potentially accessed complete message history and user information. Therefore, as I'm sure you all know, unless you're running a local version of transformers or LLMs in a contained environment, it's pretty vital that you don't share confidential information with these systems. While the AI can never forget, as ever, the weakest link are the few companies that provide these services. But that's starting to change. While setting these AI up from scratch is near impossible for small companies and immensely costly for those that can, there is thankfully a cheaper option. Just this week, OpenAI released GPT OSS, an open weight reasoning model for which the smaller version can be run on your own desktop PC. This makes it easier than ever for businesses to confidently engage with AI systems with no concern for data exposure. So, yeah, I'll end on a positive note, and that is that the technology is rapidly becoming cheaper and easier to run. And even being data aware and data conscious, we can begin to take advantage of these systems. But so much is already likely out there. And yeah, do we have any questions?